Hello, everyone. I'm Predrag, Journal Relations Specialist of Entropy Journal, and I want to thank you for joining us today on this Entropy webinar entitled Trends in Second Law of Thermodynamics. At the beginning, just a few information about the MDPI. So MDPI is a pioneer in scholarly open access publishing. It is supporting academic community since 1996. We are based on scientific exchange in all forms across all disciplines. Currently, we have more than 400 diverse and open access journals, including 459 peer-reviewed journals and 9 conference journals. All of these journals are supported by around 300,000 academic experts who share our mission, values, and commitment to providing high-quality service for our authors. About the Entropy Journal, it is an international and interdisciplinary peer-reviewed open access journal of entropy and information studies, and it is published monthly online by MDPI. About today's program, we will start with chair introduction of our Professor Dr. Roberto Zivieri. Then we will have 3 sessions. First session will be held by Dr. Silvano Tosti. Then we will have Dr. Gregory Kozan, and at the end, Professor Dr. Martin Bier. After that, we will have a question and answer session, and at the end, we will have the closing ceremony. If you are interested in submitting your research to a special issue that is linked to this topic, we would like to invite you to check the website of the special issue Trends in Second Law of Thermodynamics. Special issue editors are Professor Dr. Roberto Zivieri and Dr. Isra Medley. The deadline for manuscript submission is 15 June. You can find more information on the website or on this link or on the website of the webinar. If you have any questions for our speakers, please post them in the Q&A box at the bottom of your screen anytime during the webinar. Please also remember to add the name of the person to whom you are addressing your question. And at the end, here is the list of all of our speakers and chairs of this webinar. Professor Zivieri, now you can start. Just a second to start.
Okay, thank you very much. Good morning. It's my great pleasure to welcome and to thank the speakers and those attendees of the webinar. The webinar includes 3 presentations spanning on different topics related to the second law of thermodynamics and its applications. The speaker, Dr. Tosti, Dr. Coxon, and Professor Beer, are leading experts on the topic. In the first talk, held by Dr. Tosti, the nuclear processes are studied through a classical thermodynamic approach. Compared to the nuclear physics analysis, the engineering thermodynamics takes into consideration the change of entropy. While the fission reactions are always spontaneous, regardless of the temperature, in fusion reactions, the temperature acts as a powerful amplifier of the entropic term that at very high temperature may reduce significantly the thermodynamic spontaneity of these processes. At very high temperature, a share of the Q value is consumed to balance the entropic term, and this has a non-negligible impact on the energy efficiency of the fusion systems. In the second talk, held by Dr. Coxon, the relationship between the second law of thermodynamics and the Carnot engine is discussed. It's commonly believed that the first law of thermodynamics prohibits perpetuum mobile of the first kind, and the second law of thermodynamics prohibits perpetuum mobile of the second kind. In addition, the Carnot engine is treated as an unrealistic cycle of the ideal engine. There is one obvious and second potential loophole in the above approach. First, between the Carnot engine and the perpetuum mobile of the second kind is located the perpetuum mobile of the third kind, which is exactly prohibited by the second law of thermodynamics. Secondly, the Carnot engine is not any prohibited perpetuum mobile. In the third talk held by Professor Beer, it's investigated what happens when we move away from equilibrium and the second law of thermodynamics. When particles distribute over different energy levels, a Boltzmann distribution over these energy levels ensures. A Boltzmann distribution in a potential well also results when noisy Brownian particles move in this potential. However, they only do so if the noise is Gaussian. Levy noise is a generalization of Gaussian noise. It appears that many non-equilibrium setups in physics exhibit Levy noise. Plasma physics and astrophysics provide good examples. Moreover, it also appears in simulations and derivation that implementing Levy noise leads to non-Boltzmann distributions, violations of the Tate balance, and dissipation of energy. So let's introduce the first talk by Dr. Silvano Tosti from Nuclear Department Enea Frascati, Italy. And the title of the talk is The Rule of Entropy in Engineering Thermodynamics of Nuclear Fusion Processes. You have about 20 minutes.
So, good morning to everybody. My name is Silvano Tosti. I'm working at the NEA Nuclear Department at the Frascati Research Center. So, this is the summary of my presentation. You can see, okay. So I will just put in relationship the second law of the entropy with a case study related to the assessment of the spontaneity of fission fusion reactions. So most of the work will be focused on just on the role of entropy, the different role of entropy in fission and fusion, and in particular we will see how this classical engineering thermodynamic approach can be applied to study the spontaneity of the deuterium-based fusion reaction that are studied for the application in tokamaks device. Just a short premise just related to the difference that we had in the development of fission and fusion energy application. So we know very well that in less than 20 years, from the first evidence of the uranium fusion, people realize in less than 20 years realize the commercial reactors. Different the situation for fusion. In more than 70 years of research and development activities, we know that the fusion still face several important problems, both in engineering and in physics. So the idea is just to see if this real intrinsic difference between the development of fusion and fusion can be explained by trying to adopt a thermodynamic analysis of these nuclear processes. So just a first few words just related to the importance of the engineering thermodynamics. We know that this is a very powerful tool for the designer of the chemical and process plant. In fact, we know that when we should design any process unit in chemical process plant, we assess the change of this free energy, practically given by the change of enthalpy and the entropic term. In fact, just by using this approach, we can easily perform both the energy balances and the mass balances of the process, and then we can really, in a very powerful way, we can just do the preliminary design on the process units. So at this point, the question is, can we apply the engineering thermodynamics to the nuclear reaction? What we know is that presently all the chemical physical database have been built for the chemical processes, for the chemical reaction, in which we know that the energy level are related just to the molecular force potential and then are of the order of 1 electron volt for particle. What happens when we should consider nuclear reaction? In that case, the energy level involved in a nuclear reaction are related to the formation of new nuclear bonds established in consequences of this process. And then these energy levels are much higher than those of the chemical reaction, at the order of mega electron volt per particle. And the aspect is that all the chemical, physical chemical database disregard this nuclear reaction. So just to resume, it is possible to apply the engineering thermodynamics to nuclear reaction. The answer is yes, we can. The thermodynamic methodology works for any kind of process transformation, both chemical and nuclear. But the problem and the thermodynamic database cannot be used for nuclear reaction. So the question that now I would propose to you is just how can we calculate the change of this free energy on nuclear reaction? So how we can just assess a nuclear reaction by using an engineering thermodynamic approach. So I need also just to introduce shortly the amount of energy released by a nuclear reaction. In a nuclear reaction, we see that we realize a defect of mass between the reactants, the product, and this defect of mass corresponds through the Einstein equation to the Q value, that is to the energy released by this reaction. This is very important because we will see that the Q value will be made equal to the change of enthalpy. So at this point, when we try to approach the assessment of the nuclear reaction by the engineering thermodynamics, we should just realize to calculate the change of this free energy by using this expression. So as I said, we can just consider that the change of enthalpy can be made equal to the Q value. In fact, this is we can say that in a first approximation, all the energy released by a nuclear reaction, in the end, it changes into it. And so in a first step, we can say that the change of enthalpy is equal to the Q value. At this point, it remains to assess the change of entropy. So what we can say about the change of entropy in a nuclear reaction? If you want, in a first step, we can just qualitatively say that in a fusion reaction, light atoms merge to form a either nucleus. So this means that we are passing from a more disordered system to an ordered system. So we can say that in a fusion process, the change of the entropy is negative, and exactly the opposite situation we have in a fusion process. So it's also interesting just to see which is the comparison between the energy spontaneity analysis in thermodynamics and nuclear physics. So as we have seen in thermodynamics, we should assess the delta G, that is the change of the enthalpy minus the entropic term. In nuclear physics, we see that people consider only the Q value. So in practice, we see that in nuclear physics, people disregard the contribution of entropy. And I will show you that the role of entropy, the contribution of entropy is very important just in order to establish the difference in between fission and fusion. So in this graph, I report the energy level along the temperature for the chemical and for the nuclear reaction. So you see that, as I said, the chemical reaction are characterized by energy level, in this case, change of enthalpy of the order of 1 electron volt per particle. And also we know that the chemical reaction takes place at temperature of the order of some hundred of Kelvin. So all the chemical reactions are represented in this part of the graph. What happened for the nuclear reaction? We say that the energy level, in this case, the enthalpy or the Q value, are of the order of minus electron volt, mega electron volt per particle. So we have in the deep part, negative deep part of the graph. And also we anticipate that there is a different behavior of fusion and fission reaction. In fission reaction, we have an increase of the entropy. So by increasing the temperature, delta G decrease, further decrease, and then by increasing the temperature in a fission reaction, the spontaneity level of the process increase. Different situation for fusion reaction, in which we have a negative change of entropy. So when we increase the temperature, the delta G becomes less negative, in other words, approach the value of 0. And the other important aspect is that in tokamak, the fusion reaction takes place at very high temperature, so of the order of 10 to 8 Kelvin. So this means that at very high temperature, the entropic term can reduce significantly the amount of energy made available by the reaction, so in practice the Q value, and we will see that exists a critical, we can define the presence for the fusion reaction of a critical, thermodynamic critical temperature. In fact, you see that what happens when we increase a lot the temperature. When we increase a lot the temperature, the delta G becomes equal to 0. And so we can define for the nuclear fusion reaction a thermodynamic critical temperature can be assessed approximately equal to the ratio between the Q value and the change of the entropy. So now, starting from this consideration, we can do to perform the thermodynamic analysis of the deuterium-based fusion considered for the application in tokamaks machine, that is in application in magnetic confined plasmas. So the first reaction is the reaction between deuterium-tritium to produce helium-4 and a neutron, and giving 17 mega electron volt of energy. Then we have the two branches of the deuterium-deuterium reaction, and then finally the reaction between deuterium and helium-3. So this is the scheme, the scheme of the process that have been used. You see that I consider an open system defined by the control volume represented by the red line. Please consider that this scheme complies con the architecture of the tokamak machine, in which all the energy carried out by the neutrons is changed into it at the level of the shielding or the blanket system. So practically this scheme, in which we have deuterium and tritium entering the system, and in the end helium atoms and heat leaving the system, is very close to the real architecture of the tokamaks. So another consideration before going to the results is just to the assumption that has been done related to the fact that will be considered in the calculation of the entropy and then of the Gibbs free energy will be considered a perfect gas instead of a plasma. Please consider that this assumption is a conservative assumption. In fact, the Gibbs free energy of a perfect gas is larger than that of a plasma. So this assumption eventually produce an overestimation of the spontaneity of the reaction. So this is the formula that have been used for calculate the entropy of the system, particularly the Sackur-Tetrode formula that can be applied to a perfect gas. The initial state corresponds to a perfect gas at the plasma temperature T and the pressure of 5 Pascal, that is the pressure inside the plasma chamber of the tokamaks. The final state corresponds to a helium or tritium atoms at the temperature of the blanket shielding system, that is in this case taken equal to 700 Kelvin, and the pressure of 1 atmosphere. So interesting to also to note that in this case we can disregard in the scheme proposed, we can disregard the contribution of all the subatomic particles, because in our scheme we are representing a system, an open system, in which only atoms enter and leaving the system. So we can neglect, disregard the presence of subatomic particles. This has in particular the details of the calculation adopted. And before going to see the results, just a few words related to the other criterion important to assess the spontaneity of the fusion reaction, that is just the kinetics consideration. So in practice, as we will see later, we will compare the thermodynamic spontaneity with the probability of a reaction, with the kinetics. Just a few words about the kinetics. We know that in a nuclear fusion reaction, we have two positive nuclei that must come into contact by winning the Coulomb force. So the theory, particularly the Gamow theory, says us that there is a probability due to a tunneling effect that these two atoms can win the Coulomb force, and the probability is given by this relationship, putting in relationship the probability with the energy level of the system, or in other words, to the temperature of the system. And these are the results of this kinetic analysis for the deuterium-based reaction. I would show you that at the temperature of the tokamak, that is the vertical dashed line, we are, in this case, I considering the temperature of the tokamak of 1.5 by 10 to 8 Kelvin. You see that the deuterium-tritium reaction is the most, exhibits the most, the highest reaction rate. So going at this point, going to the results. So you will see that I represent for each reaction, the deuterium-based reaction, I compare the thermodynamic behavior. So this is, in this case, the blue line reporting the change of Gibbs-free energy, and the probability of reaction, that is just this black squared line. So you see that for the deuterium-tritium reaction, we have at the temperature of the tokamak a significant level of spontaneity. In fact, the delta G is equal to about minus 16 mega electron volt, and also we have said the probability, the kinetics is very high with respect to the other deuterium-based reaction. These are the results for the two branches of the deuterium reaction. You see that both these reactions at the temperature of the tokamak exhibit a poor spontaneity. In fact, the delta G level is close to zero. And also, as we have said, the probability of reaction is low. Finally, the third deuterium-based reaction, that is the reaction between deuterium and helium-3, has a spontaneity, thermodynamic spontaneity similar to that of the deuterium-tritium reaction. In fact, the delta G at the temperature of the tokamak is around 17 minus 17 mega electron volts. And on the other end, the reactivity, the probability of reaction is lower, is similar to that of the deuterium-deuterium reaction. So in this graph, if you want, you can see compared all the four reactions. I would just note to you that the critical temperature of the two deuterium-deuterium reaction, the red and the green line, you see that the critical temperature are very close to the temperature of the tokamak, just representing the fact that these two reactions have a poor thermodynamic spontaneity. This is a final conclusion, just a final aspect to be considered, and it is the impact of this analysis on the design of fusion reactor. So it's important to consider that when we will do the energy balance of the tokamaks, we should consider the effect energy made available, that is not the Q value, but is the Q values minus the entropic term. So, for example, for the deuterium-tritium reaction, we should consider that the energy made available is 16 MeV and not 17.6 MeV, that is the Q value. So this is very important, because this means that in the future design of the tokamak machine, we should consider this real effect, and then so you see that the contribution of the entropy could be not negligible. These are the conclusion. I would just to say 2 words about the future works. We will try to assess the entropy through the kinetic theory, that is assessing the change of entropy from the distribution function. Other study could be to be related to the study of the fusion, the spontaneity of the fusion in the star, where we have different plasma regimes and so on. So we should find the correct way to assess the entropy. That's all. I thank you, all of you, for attending this webinar, this presentation. I wish thanks particularly Professor Luigi Marrelli, my colleague Antonio Pietropaolo, and Professor Roberto Zivieri for supporting in my work. And these are some reference related to papers available around this work. Thanks again.
So let's thank Dr. Tosti for this nice and interesting presentation, also on the application of entropy on the second principle. And now we pass on to the second talk. And the second talk will be held by Dr. Koczan from Warsaw University of Life Sciences, Warsaw, Poland. And the title of the talk is, Does the Second Principle of Thermodynamics Prohibit a Real Carnot Engine?
Okay, hello everybody. Welcome. I am Grzegorz Marcin Koczan. Marcin is my medium name. First name Gregory, simple say Gregory. Grzegorz Gregory, simple say. My alma mater is, I have 2 alma maters, Warsaw University. It's my studies and doctoral studies, and second alma mater is Warsaw University of Life Science, where I defended doctoral thesis, and I work now. Both universities were founded in 1960. It is 8 years later, before famous Carnot work, 1924. Presentation objectives. The first, scholium. I want give main ideas to create real Carnot engine. I want preparing for publication of a real Carnot engine model. I think that in future maybe other people build this Carnot engine, maybe based on my model, which I planned published in the future. And next, clarification, the second principle of thermodynamics. What about principle versus law? Principle is general logical rule, universally, but may have exceptions. But law in physics, it's a mathematical formula to which physically quantitatives obey without exceptions. Questions? The second rule of thermodynamics is principle or law. I think that it is principle. Sorry. Okay. And for example, three examples that exist exceptions to second principle of thermodynamics. First examples is negative entropy fluctuation at equilibrium states. Second example, negative entropy evolution in prepared state with opposite velocities. First and second examples is indisputable fact, indisputable fact, I think. But the third examples is maybe disputable, but it is heat flow in refrigerators and heat pumps, or projectile heating, which is opposite to Clausius' statement. I have two publications about second principle. The first publication 2022, it's my Elon publication, proof of equivalence of Carnot principle to second law of thermodynamics and non-equivalence to Clausius first and Kelvin principles. And second publication with Roberto Zivieri, 2024, a revision of the phenomenological and statistical statement on second law of thermodynamics. Second principle, now I formulate second principle as a prohibition of various perpetuum mobile. First formulation of Kelvin Oswald. There is no perpetuum mobile of second kinds, i.e. heat engine with 100% efficiency, therefore eta efficiency is less than 1. Yes, of course, this statement is true, but very insufficient. More sufficient is this formulation. There is no perpetuum mobile of third kind, i.e. heat engine with greater efficiency than reversible engine, Carnot engine. Therefore, eta less or equal Carnot eta efficiency. Note, this statement is equivalent to principle of non-decreasing entropy. Second principle of thermodynamics versus Carnot law, Carnot engine, sorry. Of course, second principle not prohibit Carnot engine. It is possible that eta is equal, theoretically, equal eta C, Carnot efficiency, or approximately equal. It means that Carnot engine is not any perpetuum mobile. Now I see thermodynamical cycles between heat reservoirs. Classical schema engine, heat engine, yes, cooler, which have temperature T2, heater with temperature T1, and engine. In the left, heat engine cycle diagram. In Clausius variable, P pressure, V volume, we see green figure. It's this cycle. Most workful cycles, except Carnot. For example, Stirling cycles have large field of work between isotherms of heater and isotherm of cooler. Not that this work is significant larger than similar cycles, for example, Otto, Brighton, Diesel, Humphrey, and Lenoir. Similar situation is for Ericsson cycle. Here, I now present a real Stirling engine. Here is GIF Stirling Alpha engine. This patented 1960. This is the same year when founded my universitas. Yes, it's coincidence, interesting coincidence. Here it's real model. This is hot cylinder, cooler cylinder, fire, Y wheel, connected rods, and alternator. I have here this engine, and I have fire, but I now can't time for presentation, but maybe later somebody ask about it. Let's go next. Unlimited Stirling cycles, limited analysis. For example, Stirling circle, this formula for work, and volume 2, if volume 2 tends to infinity or volume 1 tends to 0, then this work tends to plus infinity. It's interesting results. In this same time, efficiency of this cycle tends to Carnot efficiency. It's good results too. For example, note, for example, for Otto, Brighton, Diesel, Humphrey cycles, in this same situation, efficiency tends to 0. If efficiency tends to Carnot efficiency, works tends to 0. This shows that it's not optimized cycles. Definition of comparative cycles for real Carnot engine. The gas equation for formula of equation of states for isochoric and isobaric. It's practically its linear function. That's why we defined easy one standard of relative error, delta P division by P, delta V division by V, delta T division by T equal epsilon. For example, epsilon 5%, for example. Yes, that's why we have cross error, and we can define practical, realistic, experimental, verified, falsified cycle. This real Carnot cycle, quasi Carnot cycle, CVs. Yes, it's two isothermas and two adiabatic, but we have cross error, which defined something deviation about exact Carnot cycles. Yes. How to make a real Carnot engine? Our challenge my challenge is replace Stirling Alpha engine to real Carnot engine. This mean exactly replace isohorse to adiabats. How to make these adiabats? Firstly, in Stirling Alpha, we must widening cold cylinder. That's its volume V. It's bigger than volume 3 of hotter cylinder. In the first which we have to doing. Secondly, we need use complex connecting rule, complex fly wheel or cam mechanics to doing more complex kinetic of process, which do adiabatics. Next ideas is fast is differentiated isotherms, which mean isotherm who have not equal temperature as hotter on here in cooler. This difference temperature delta T T1 or delta T2. Thanks to this difference, this isothermas can working faster. It's important key. This cycle I propose my terminology proposition, yes, real Carnot engine cycle, quasi-Carnot cycle, irreversible Carnot cycle, and or differentiated Carnot cycle. This I called it irreversible Carnot cycle because it's working in this difference temperature delta T. It's a reason that's why it's not exactly irreversible reversible cycle. Sorry. I can. Oh, okay. Efficiency of differentiated Carnot cycle. If we change temperature minus and or add delta T, we have standard formula for efficient Carnot engine, and we change this formula exactly this way. Note the differentiated cycles may be a perfect Carnot cycle. Maybe it is perfect Carnot cycle, but it will be irreversible due to the heat reservoirs, not due to its own shape. Shape of this quasi-Carnot cycle is exact, maybe be exact perfect Carnot cycle, but exactly it's not reversible cycle. Future heat sources. The first in my specialist, for example, wood-fired rocket stove, anti-smoke after burning. This system We see here after burning schema, these columns shaft were after burning. Next, we see building something like stove. The first is core, and next insulated coat here, and our outer coat, the biggest one. Another heat sources, it will be nuclear sources. For example, like this, we see nuclear reactor in right side. In the middle, we see Stirling alpha engine, and left we see alternator. About Stirling alpha engine, we see two piston, this piston and this piston, and two space for gas compression, compression space, and expansion space. Okay, I concluded. I have five conclusions. First, real Carnot engine is not prohibited by second principle of thermodynamics. Second, real Carnot engine may be an improved Stirling alpha engine. Three, the cold cylinder should be wider than the hot cylinder. In Stirling, it's our Carnot real engine. Four, adiabats can be realized by more complex connected rods or cam mechanics. Five, fast isotherms can be realized as differential isotherms. The end. Thank you for attention. This presentation will be available on Reset Gate. Okay.
Thank you very much for this very nice presentation and challenging also presentation. And now we pass to the third talk. The third talk will be held by Professor Beer from Department of Physics, East Carolina University, Greenville, USA. And the title of the talk is What Happens When We Move Away from Equilibrium and the Second Law.
All right, well, thank you very much. And I want to thank the organizers for inviting me here. So I'm Martin Beer. I'm working in East Carolina University. That's in North Carolina. Yeah, we just saw a talk on the more fundamental aspects of entropy, the second law. I'm more on the applied side, and basically for the applied people, equilibrium thermodynamics has all been solved more than 50 years ago by Onsager, and even close to equilibrium. We have the Onsager reciprocity relations that do a perfectly good job. Now, a lot of our work has been towards what happens when we're far away from equilibrium. The second law gets messed up. Yeah, try to get an understanding. Do we have any equivalent for the fluctuation dissipation theorem? So yeah, a lot of the results are kind of ad hoc, and in my talk I will necessarily be not showing you a general theory, but some specific cases. All right, let's first remember equilibrium thermodynamics. We all know the Boltzmann distribution. You have a bunch of particles. There's a certain amount of energy. These particles are colliding, exchanging energy. what you get in your reservoir in the end is a Boltzmann distribution. A Boltzmann distribution over the energy levels, which here are discrete. It's not that hard to calculate that the Boltzmann distribution actually maximizes the entropy. It is the macro state that has the most microstates. You have a similar logic applies when you don't have discrete levels, but when the energy varies continuously. So let's take this parabolic potential and you put a whole bunch of Brownian particles in that potential. In this case, the Boltzmann distribution is going to be a Gaussian distribution on X, here it is. Now you also get a Gaussian distribution if you just consider one particle in that parabolic potential, and that particle is then subject to Brownian kicks, to noise, and we let that noise at first approximation, due to the central limit theorem, etc., we let the noise be Gaussian, meaning that the kicks that the particle gets have magnitudes that are Gaussian distributed. So this is the Langevin equation. The first term here on the right-hand side describes the force due to the potential. The second term is a stochastic term. Every time step, you draw a number from a Gaussian distribution that gives you the kick size. In the end, with Gaussian distributed kicks, you get a Boltzmann distribution again in the potential for this one particle. This is also known as the Ornstein-Uhlenbeck process. And for the Ornstein-Uhlenbeck process, you relax to that Gaussian distribution. All right, this result is only valid if that noise term is Gaussian distributed. What happens when you move away from there? And already 100 years ago, the French mathematician Paul Lévy studied that. First, going back to equilibrium noise, with Gaussian noise, the tail of the distribution, it's a nice bell-shaped curve, but then you converge to the horizontal axis. For Gaussian noise, that convergence is fast. It's exponential. So with Gaussian noise, you never get really big kicks. You never get outliers. This is what it looks like. You have that when I simulate that Langevin equation that I showed in the last slide. Also, and this is sort of interesting, at equilibrium, there is no arrow of time. And that means that you cannot really discriminate here. There's no mathematical way to discriminate between the forward time direction and the backward time direction. If you play the movie forward or play the movie backward, you can't discriminate between that. All right, Lévy stable noise, or also called alpha stable noise. It's the brainchild of Paul Lévy, French mathematician. You now do not have an exponential tail. You have a power law tail. The convergence now is much slower. And this means you get outliers. So here is actually the formula at the bottom for these tails. I'm not going to show you the general formula for the alpha stable distribution. It looks horrendous, and I don't want to overwhelm you with math. It's also a bell-shaped curve, but again, the tails are power law tails. You get outliers, and now this is what you see. And you can clearly see the outliers here, yeah? There's a really big one here. It shoots up to 300. What you also see here is that the time reversal symmetry is broken because you get an outlier kick and look, you're shooting up, but then the sliding down is much slower. So you can distinguish now between time going this way and going backward. Now, the alpha stable noise, the Levy distribution, it's not just the brainchild of a French guy. It turns out we actually see it in reality. So I'm just going to give you one example, but there are numerous. I pulled this picture from the web. This is the sun. They call it equilibrium, but of course it's not. It's not a thermodynamic equilibrium. Inside the sun, there is a permanent thermonuclear blast occurring. But from the outside, there is the gravitational weight of all these layers weighing back on the thermonuclear blast. And in the end, these two pressures balance out, and that's why the sun looks the same every morning. So this is steady state, but there is continuous energy conversion and energy transport. Now you can actually well model this system by that parabolic potential with the Brownian particle in there. And that is on my next slide, I explain that. So first imagine that on the inside here, suddenly your thermonuclear blast there has an increased reaction rate. Well, that means that the temperature is going to increase and the pressure is going to increase. That means that that core is going to expand. But as soon as you expand, things are going to cool down. Also, the density is going down. That in turn will cause the fusion rate then to decrease again. So in the end, the system is driven back again to the minimum. So there's noise, but there's this permanent force driving you back to the minimum. In other words, you can model the sun as this Brownian particle in a parabolic potential. Well, we can see some signatures of what's going on inside the sun. If we measure solar soft X-ray intensity, solar soft X-rays, these are X-rays in between 1 and 8 angstrom. We've had satellites measuring the intensity of these X-rays. They've been doing measurements for decades, and they're sampling every 2 seconds. All these data are publicly available, and yeah, we can have lots of fun with them. So here we actually recorded 20,000 seconds of these solar soft X-rays. And yeah, you can see this looks exactly like what we had on that third slide with Levy noise. Let's go back here. Yeah, shooting up, sliding down. Oh, that's what's happening here. Yeah, so these, when they get really big, these are called solar flares. So obviously, what's happening inside the sun is not Gaussian noise, it's Levy noise. And in general, Levy noise is what you see when you don't have thermal equilibrium, but instead you're out of equilibrium because energy is transported, energy is converted. We actually had an article on this a couple of years ago. This shooting up and then sliding down, you can use that as a way to estimate that alpha in your expression for the alpha stable noise. The alpha is generally, it's between 0 and 2. And actually, once you reach 2, alpha is 2, you have Gaussian noise again. So you can think of alpha stable noise as a generalization of Gaussian noise. And again, systems that convert or transport energy, i.e. non-equilibrium systems, they generally exhibit Levy stable noise. I gave you one example, but there's many more. Also in physiology, the heartbeat exhibits Levy stable noise. Economics, already in the 1960s, Mandelbrot discovered that the variation of stock prices, there we have alpha stable noise. Plasma physics, climate science, we see it a lot. And with all of that, you can ask yourself, look, the thermodynamics, the statistical mechanics textbooks are full of examples where you use Gaussian noise. But what if in these examples, what if we replace the Gaussian noise by Levy stable noise? How is reality going to look then? And well, I only have time to show you one example. I'm taking 2 reservoirs and I'm putting 50,000 particles in here. So there's a big reservoir on the left and a small reservoir on the right. And in between is a small opening. And there's 50,000 particles in there doing Brownian motion. If the displacements of these Brownian particles are Gaussian distributed, you will end up with equal concentrations on the left and right. And that's not hard to understand, because when the noise is Gaussian, when the displacements of the particles have a Gaussian distribution, you don't get any outliers. So all that matters for transport, for transitions from one reservoir to the other, or from the other to the one, all that matters is a small region in the neighborhood of the opening. And that region is symmetric. So you, in the end, with equal concentrations, you get just as many transitions from the left to the right as from the right to the left. Equal concentrations. Okay, now we let the displacements be alpha, have an alpha stable distribution. And now the outliers, the large jumps, they get statistical significance. With alpha stable noise, you have to take into account the transitions that occur when you are far away from the opening, and a big outlier Levy kick is going to shoot you right through the opening. And you can understand now that there is now more ways to go from the large to the small reservoir as that there are from the small to the large reservoir. You can hear that you can go from that dashed semicircle straight through the opening to the other one. And there is no such semicircle on the other side. So you can easily intuit at this point that with alpha stable distributions, the concentration in the small reservoir is going to be larger. And by the way, we did the simulation. We did it with 50,000 particles in here. We let the inner wall, the semicircular walls here, they were sticky, meaning that when a particle hits the wall, it gets stuck there, and only a next Brownian kick is going to move it away from that wall. On the other hand, that these vertical walls, they're reflective, they bounce. This may sound strange, but I have to make these assumptions so that I can not just rely on Monte Carlo simulations. With these assumptions, I can actually do some very good approximations with some integrals. And we're all working it out in an article in Entropy in 2022. And here you see the result. And indeed, you see, yeah, the active particles, the Levy noise, we used alpha is 0.8. The big circle has twice the radius as compared to the small circle. And the particles accumulate near the wall. And also you have a bigger concentration in the smaller reservoir. We recorded the concentration along this line. And that led to the red curve here, which is a histogram. The dashed blue curve results from the integrals. So this means we're doing it right. Yeah, the integrals and the Monte Carlo simulation, they give us the same curve. And this is actually also a result that is known from practice. If you have self-propelling particles or particles that make big jumps, they tend to accumulate in the nukes, in the corners, and near the walls. All right, now I'm going to sort of free think again about an interpretation. And I like to think of this non-homogeneous distribution. And by the way, this is against the second law, yeah? You get the highest entropy with a homogeneous distribution. But here we see a lower entropy. I like to think of this as a dissipative structure. The idea of a dissipative structure comes from Prigogine, from more than half a century ago. It means you have a low entropy self-organization in your system, but that low entropy self-organization helps you to dissipate power, to transfer energy faster, i.e., in the end, to produce more entropy. So it's like an investment. It's you create some low entropy to produce more entropy in the end. Now, in the way you can think about it here is that, look, when you have your Gaussian distribution for Brownian particles, the standard deviation of that Gaussian is associated with the temperature. With the power law tail, the power law tails that we have for Levy noise, the standard deviation, the variance, it is infinite. So technically you have an infinite temperature. However, you cannot get infinitely big jumps in this system. When you apply Levy jumps in this geometry here with the two semicircles, your tails are truncated. You cannot make any jumps that are bigger than the system size. So that gives you a temperature again. That gives you it cuts off the tails and you have a temperature again, but it's still a high temperature. Now, this non-homogeneous distribution, these particles accumulating near the wall and at the corners, that means that you facilitate more heat transfer from inside the system to the outside. Now, in my equations here and in the simulations, there is no heat transfer. But as an applied physicist, you want to go sort of beyond just the system and think about the larger context. And this non-homogeneous distribution, it facilitates transport of energy. Now, we may not be talking here, and this will be the last slide, just about abstract things. 30 years ago, I was at the University of Chicago, and there were lots of people working on the so-called coffee ring effect. You take a drop of coffee and you drop it on a white table. It will evaporate, yeah? Now, it turns out that the coffee powder in the end will accumulate at the rim of your drop. Lots of thought has gone into explaining this. All the big University of Chicago physics professors were having meetings about it. There's a Wikipedia page about it, lots of articles. The mechanism that I showed in my previous slide has never been considered, but it may well be at work, because an evaporating drop, it's not at equilibrium. It's out of equilibrium. You may get the levy jumps that I talked about, and the levy jumps drive these particles, these coffee particles, to the outside, to the rim of the drop. The very first, very interesting presentation in this webinar was about nuclear fusion and nuclear fission. I may take some issue with what was presented there. A nuclear fusion reactor is not at equilibrium. The whole idea of temperature may not even apply. You may get very much what I showed you in the previous slide, a non-homogeneous distribution of your particles in your your toroidally shaped tokamak reactor. An inhomogeneous distribution could well lead to instabilities, and that may be something engineers may have to take into account. Finally, medicine has now come to the level that we're building tiny robots that we can inject in human beings. And I'm talking about devices that are smaller than 1/10 of a millimeter, and they can move along in the blood flow. These micro swimmers, these micro robots, are designed to do all sorts of things like diagnosis, tumor removal, drug delivery. However, the blood flow and any sort of fluid flow in the human body, it's non-equilibrium. And these micro swimmers and micro robots may well end up being stuck in all sorts of little corners. Something we have to, they may not distribute homogeneously. That's the bottom line message here. All right, I am at the end of my allotted time. I don't want to end before acknowledging my co-worker here. He was my grad student. He meanwhile got his PhD. He was a very good grad student. He meanwhile fled the hysteria going on in America now. He's working in Vancouver. Yeah, so I'm grateful to him. At this point, yeah, questions, comments, criticisms. I think I was the last presentation on the webinarium. Thanks for your attention.
Really, let's thank Professor Beer for this insightful and soulful and so clear presentation. Really, very, very, very interesting. Thank you very much.
Thank you.
Now session is open for discussion. There are some in the chat, and there are some. I can read some questions. For example, one question from Dr. Coxon to Dr. Tosti. I see in the webinar chat. Is the total change of entropy for fusion reactions, not only the products, positive?
Yes, thanks for the question, first of all. So what we can say that if we consider a nuclear fusion reaction, specifically, we should, in principle, you see that we should consider also the presence of subatomic particles. This means neutrons, protons, and so on. So, so far, we don't have any, in classical engineering thermodynamics, we have no tools just to perform this calculation. So strictly, I cannot answer to your question in these terms. But if you want, I would highlight, on the other hand, the approach that I have used in my study. In that case, I consider not the reaction, but I consider the system. So I consider a tokamak as an open system, and then in that case, for the system considered, you see that I don't have subatomic particles, so I can disregard the subatomic particle. So in that case, I can say that for that system operating with that process, I can say that the change of entropy is negative. So the consideration of a fusion nuclear reaction taking into account also the subatomic particle will be the object of the future works, the next work, in which we would try to consider to assess the entropy of a nuclear reaction by using by calculating the distribution function, so by using the kinetic theory. In the past, there was some attempt to do this, so we would just restart from this from some preliminary works in this way, and the idea just to complete the works in this way.
Okay,
So
thank you very much. So
can I add?
Can
So that
I
means
talk? I am first. Thank you for answer, Silvano Tosti. I comment. I think I agree that change entropy is negative for products, but I think that in fusion reaction we have a lot of energy, a lot of photons, and maybe if we calculate these photons, I claim, I think that entropy change is zero or positive. Do you agree?
Yeah, okay. So we can expect this, but I would just say that on the other end, on the engineering point of view, what is important just for the application, for the engineers, if you want, for the designer of the machine, is just important to account that the energy made available is not the Q value, because presently all the activities related to the design of the tokamak machine in the main project in Europe, also in the world, the energy balance are based on the assessment by using the Q value. So that people say, okay, we have available the energy corresponding to the Q value. Please pay attention that you cannot use the Q value, but you should reduce the Q values by the entropic term. And then this aspect has been so far neglected. You see that for the deuterium-tritium reaction could be not a big change, but anyways, estimated about around 10%, could be not so negligible.
okay, many thanks. Many thanks for this. And Professor Beer is asking. So
yeah, it was because Grzegorz mentioned the photons, but there's also like neutrinos being released in these nuclear reactions. It's going to be an interesting project to figure out how, yeah, all these subatomic particles, how they contribute in the end to the entropy. Yeah, that's my comment. It's a can of worms, but it should be calculable in the end.
Yeah. Okay. Yeah. So I fully agree that this work should be followed by more detailed analysis of the change of entropy that take into account all the other particles of energy forms that we have in a nuclear reaction. But anyway, I would like also coming to the comment in your presentation, Martin. Sorry if I do say that. Obviously, a tokamak is not a plasma, a deuterium based plasma in a tokamak obviously is not operating under equilibrium condition. I agree, but I would also come back to the consideration about the engineering thermodynamic analysis that is a powerful tool. So you know very well that all the chemical units, the process units in a chemical plant, for example, a distillation column, a reactor, as you want, are units that are not operating under equilibrium condition. But anyway, all these units can be preliminary designed by engineering thermodynamics, because engineering thermodynamics give us important information about the operating condition. For example, ammonia synthesis. The engineering thermodynamics says us that we should operate at high pressure, at that temperature, and so on. So I would say that this aspect, the engineering thermodynamic approach to the study of nuclear machine has been so far neglected. And then we can anyway extract some important information for addressing better the design of, and then the experiment also in this field.
Okay, thank you very much. And then there is another question by Dr. Coxon to Professor Beer. Is how do you explain huge numbers theorem means that all distribution tends to normal distribution?
Yeah, that's a good point. And I didn't have the time to address that in my presentation. So thank you, Grzegorz, for bringing it up. Indeed, if you look at the cumulative effect of a whole lot of stochastic processes, the central limit theorem then tells you that you get a Gaussian. If you take like 100 dices and you throw them and you add all the numbers and you throw them and throw them and throw them and throw them again, all 100 of them, in the end you get a Gaussian distribution around, it's 100, so around 350. This, however, only is true if the standard deviation, if the variance of each constituent distribution is finite. As soon as you have a distribution with an infinite variance, and these are not pathological distributions. Already Huygens came up with a distribution with an infinite that had infinities in the 1600s or 1700s. As soon as you have infinite variances, and that's what you have with Levy stable noise, with Levy distributions, yeah, the central limit theorem, or what you call the huge numbers theorem, is out of the window. Yeah, that's yeah, I could elaborate on it, but this answer hopefully satisfies.
In other words, Levy noise is break assumption of huge number theorem. Yes, I
It's
would
an
understand.
extension. It is an extension of
Extensions.
the theory. It's an
Okay,
extension
thank
when
you.
you have infinite variances. And indeed, in the early 1900s, this was a game for Paul Levy. It was a mathematical challenge. But yeah, as I said in my talk, we see Levy stable noise. We see these distributions now, yeah, in a lot of cases. Very simple cases from physiology, from yeah, solar physics, as I showed you.
Okay, thank you very much. But we have other questions from. There is another one. It's for Dr. Coxon from Casper Helder, Dr. Casper Helder, and Can you read it? It's a long question, but it's in question and answer. And again, another from Dr. Helder to Professor Beer in question and answer.
I don't
Can you
see it on
check?
my webinar chat.
Can you check in question and answer, Dr. Coxon?
Uh-huh.
It's a
Is
long
it in-
question. It's a long, okay, but the
Ah.
question is at the end of the. Can you see it?
I don't. It's not in the chat.
I say to Dr. Coxon, can you see the question by
It's a
Dr.
question
Helder?
and answer box.
I don't see any question from any question. I don't see any question.
You will see the Q&A box beside the share button.
In the QA box. QA box.
Yes. And there's 4 questions inside.
Everyone can see it.
Just right beside the Q&A button.
QA box in the bottom. In the bottom.
Oh, okay. Yeah, I see.
Okay.
Okay, I see this question. Please,
Okay.
somebody to read this question, and I next answer. Okay.
So do we want to read it?
Please.
So thank you for your presentation, Dr. Coxon. You wrote that the Stirling cycle covers a larger work area than the Otto Brayton, Diesel, Humphrey, and Lenoir cycle. In my opinion, when these cycles, including the Carnot and Stirling cycles, are configured with an ideal gas, and when only the amount of exchange thermal energy and the corresponding temperature at which the transfer occurs are considered during the completed cycle, applying the closest entropy formula, yields 0 for all of them, delta S equal to 0. This could suggest that in principle, the Brayton cycle is as thermodynamically reversible as the Carnot cycle. What is your view on this aspect related to delta S equal to 0?
Yes, exact, perfect Carnot cycle is reversible cycle, and that's change entropy is 0. Okay, but I presented cycle which seem exactly like Carnot cycle, but there is there are irreversible isothermas, which working on different temperature. Hotter have a little more temperature than gas. Why? Because there this isothermas, this process would be faster, because isothermal process is very slow, and we get this differences temperature. We can faster process, and we have produce some entropy. Entropy produce no in the gas. In cycle occurs periodic cycle, entropy gases is of course change entropy is 0, but change entropy of heater or air cooler total is add in process who I show. Okay.
Okay, thank you very much. And there are a couple of questions for Professor Beer. One from Tomor Haksimali, one of the attendees, and the question is: we replacing Gaussian noise with the Levy noise be analog to replace the Boltzmann entropy with Sallis entropy? Sallis entropy.
Yeah,
I know it's something.
I know. I have never really studied Sallis
Mm.
entropy in detail. I know that there's all sorts of correlations that he adds to systems that change outcomes. I don't know. I would have to look at it. Maybe there is a link, but I'm not an authority on Sallis entropy, and I couldn't, off my head, say something very meaningful here. Yeah, I can. By the way, I can read the question and answers now. I did pull up the.
It's in question and answer, and then there is another question. Thank you, from Dr. Kasper Helder for Professor Beer. It's a long question, but okay, I read it. Is it correct to say that? Can you read it? Thank you. Thank you. Yeah. Can you read it in question and answer?
Yeah, you want me to read the question, or shall I give the answer and summarize the question?
If you can give an answer to this long question, summarize it and give a brief answer. Yes, because it's a very long question.
Okay, yeah. So the question is about, look, in the interior of the sun, there are the nuclear reactions, very high temperature, but then that energy is transferred. The heat that is generated is transferred. And that is what heat in general does, no? Following the second law. It spreads out, it homogenizes. So then the question, if so, it would seem that the energy processes in the sun are highly thermodynamically irreversible. Well, indeed, the spreading out of the heat, that is an irreversible process. Applying Clausius entropy to that transfer from the core to the surface, the numerical outcome appears to support this view. Well, when heat spreads out, when it homogenizes, that increases the entropy. That is why, look, the interior of the sun is millions and millions of degrees. The radiation that we see from the sun comes from the outside, from the very surface of the sun. That is about, I think, 5,000–6,000 degrees Kelvin. That heat from the interior has spread out. What we see is black body radiation corresponding to about 5,000 degrees Kelvin. That's why when I showed you this graph for the solar soft X-rays, that is really a signature of what's going on in the interior. The non-equilibrium processes that are going on closer to the core. But yeah, that comes, it's sort of separate from the homogenization of the heat. I hope that answers the question.
Okay, thank you. And there is another question, but the attendee is not anymore here, so you can type an answer if you want. Here, it's from José Miguel Rubi Capacchetti. You can type an answer here, I don't know. It's a question to Professor Beer. It's something like related to a microscopic interpretation of Levy noise. Microscopic interpretation of Levy noise.
Actually, yeah. You want me to say something, or shall I type an answer?
I think you can say
also,
it.
It's not anymore here.
Sorry. I think it's okay to say it, as for other questions, the recording will be online. So Dr.
The
Capacetti
online,
may
okay.
check
Yes.
the recording later.
Okay.
Thank you.
Okay. Thank
Okay, so I can answer the question because it's a very good question.
It's a very good,
Why?
yes.
I mean, why would you have in a non-equilibrium situation these large jumps? Why do you get Levy noise? There is no general theory of it. If you would come up with a good general theory of it, you can also book your flight to Stockholm for next December. The thing is, whenever there's non-equilibrium, we just notice Levy noise. And I showed you one example, but you write an article about this, and in your reference list, there's a whole lot of them. As I mentioned, the heartbeat, the climate record. Whenever there is energy being converted or being transported, we see Levy noise. We see these outliers. Why? There's no general theory of it. That's why in my talk, I first showed you a convincing example of, look, you can't be any more non-equilibrium as inside the sun. There's a huge amount of energy being generated there. We see Levy noise. And then the next question you can ask is, hey, go back to the textbooks and replace Gaussian noise by Levy noise. What kind of things do you see? But indeed, why Levy noise with non-equilibrium? There's no general theory. It's just phenomenological. But it's okay to work like that.
Okay. Many thanks. So questions are finished. And so I can give in a few my closing remarks. We are very grateful to you all for taking time off from your busy schedules to attend the webinar. I see participants. Thank you for having attended the webinar and for your insightful questions and comments, which heated discussion and gave rise to open questions and possible future collaboration. A special thank goes to the speakers for their commitment in preparing these nice presentations, outlining the recent advances on the second law of thermodynamics. I think that this webinar has been a good occasion for an exchange of ideas, and we've seen a lot of questions and opinions among experts on such a fascinating argument. Thank you very much to everyone.
Thank you, Dr. Zivieri, and thank you all of for follow all of our speakers today. I think it was very good webinar. We had very fruitful discussion at the end. I'm very happy to see that, and I hope that all other participants enjoyed and heard something interesting and new for the end. So to thank all of you for participating today, and just to add that in the chat I added some links so all participants can download.
Okay.
Then we will make this recording of the webinar. It will be as soon as possible available at the website of the webinar, and also all participants can check some other upcoming webinars. Thank you very much for joining us today, and as I said, all other details will be at the website. Thank you very much.
Okay.